All right, we are in Chapter 6, Exponential and Logarithmic Functions, and today we'll be talking about Section 6.6, Exponential and Logarithmic Equations. In this section, students will use like bases to solve exponential equations, use logarithms to solve exponential equations, use the definition of a logarithm to solve logarithmic equations, use the one-to-one property of logarithms to solve logarithmic equations, and solve applied problems involving exponential and logarithmic equations. So it looks like a lot, but basically we're learning how to solve exponential equations a couple different ways. We're learning to solve log equations a couple different ways, and then we're going to use that to help us solve applied problems. Okay, so there's something called a one-to-one property of exponential functions. So it says for any algebraic expression s and t and any positive real number where b doesn't equal 1, then b to the s equals b to the t if and only s equals t. So that, hopefully that makes sense. This b to the s can only equal b to the t if both bases are the same. They can only equal if s and t are equal to each other as well. So we can use that fact to help us solve certain exponential functions. So given an exponential equation with the form b to the s equals b to the t, where s and t are algebraic expressions with an unknown, solve for the unknown. So use the rules for exponents to simplify if necessary, so that the resulting equation has the form b to the s equals b to the t. Use the one-to-one property to set the exponents equal to one another, and then solve the resulting equation for the unknown. All right, so let's look at this first equation. 6 to the 9x minus 8 equals 6 to the negative x. Okay, so what they're saying here is that we have like bases on the left and the right. So if 6 and 6 are equal, then that means this exponent on the left has to equal the exponent on the right. So we're going to use that fact to help us solve for x. So all we did was we set the exponents equal to one another, because if you think about it, they have to equal one another or this statement here is not true. The only way this can be true with the bases being the same is if the exponents are also equal. So we set the exponents, negative 9x minus 8 equal to negative 6, and then we're going to solve. So I'm going to add 9x to both sides, and I'll get negative 8 equals 8x. Divide both sides by 8, and we get x equals negative 1. All right, and you can always go back. That's the beauty of equations. You can go back and check your answer by subbing in the value we found for x, and that value was negative 1. So I have on the left, I have 6 to the negative 9 times negative 1 is positive 9 minus 8. On the right, I have 6 to the negative 1, which would be positive 1. 9 minus 8 is positive 1. So 6 to the first equals 6 to the first. So that is correct. All right. So you guys try it right here. Pause the video, attempt the problem, and then unpause when you're ready to go over the solution. Okay. So you notice that the bases are the same. 5 and 5 are equal. That means 2x must equal 3x plus 2. So now you're going to solve. I would subtract 3x on both sides to get the x's on the same side, and I get negative x equals 2. That means if I divide both sides by negative 1, I get x equals negative 2. And if you plug that back into the equation, it does work out. All right, so that was solving it using the one-to-one property for exponential functions. So now we're going to use like bases to solve exponential equations. So given an exponential equation with unlike bases, use the one-to-one property to solve it. So basically what you're going to do is you're going to rewrite it so that it does have like bases, and then follow the same guidelines we did for the last examples. So first you're going to rewrite each side of the equation as a power with a common base, and then you're going to follow, if you check out steps 2 and 3 and 4, they're the same as steps 1, 2, and 3 here. So the only difference between this new example and the ones we did here is that the ones we did earlier have like bases. Now we have unlike bases. But what we can do is 4 and 16 are both powers of 4. They're also powers of 2. So I could rewrite them both as a common power of 4, or I could rewrite them both with a common power of 2. So let's start with 4. So 4 to the x plus 2 is already a power of 4, where 4 is the base. But 16, so on the right hand side, 16 to the x plus 1, instead of 16, I'm going to convert that to a power of 4. 16 is really 4 squared. Okay, so that is the first thing that you do, is you're going to rewrite the problem, and so that you're rewriting each side in the equation as a power with a common base. So the common base I chose was 4. So now we are going to simplify if possible. So on the left, we're going to leave it 4 to the x plus 2. On the right, we have 4 squared to the x plus 1. Basically, what you do is you use laws of exponents, which says if you've got a power outside of a power, you multiply. So I'm just going to multiply 2 times x plus 1. And I'm going to get 2x plus 2. Now that the bases are the same, that means that the exponents are equal. Otherwise, the statement's not true. So I can set my x plus 2 equal to 2x plus 2. And I would, it's up to you at this point, what you want to get rid of, as long as what you do to one side you do to the other. So I would subtract 2x on both sides, and I would get negative x plus 2 equals 2. Subtract 2 on both sides, and I would get negative x equals 0. That means x equals 0. Alright, so I just want to show you that there is another way to approach it, because 4 and 16 have another power in common, a base in common, and that would be 2. So I could rewrite this as 4 to the x plus 2, but write 4 as a power of 2. 4 is really 2 squared. And 16 to the x plus 1, 16 is really 2 to the 4th power. And then we'll do the same thing. We'll do the rule where we multiply the exponents. So this is really 2 to the 2x plus 4. And on the right I have 2 to the 4x plus 4. And then now that we have them written as a common base of 2, we can set the exponents equal to one another. And I'm just going to subtract 4x on both sides, and I get negative 2x plus 4 equals 4. When I subtract 4 on both sides, look what happens. Negative 2x equals 0. When I divide both sides by negative 2, I get 0. So either way, you are going to get 0. Okay, so that's how you solve exponential equations, where you can rewrite each side with a common base. Alright, so you guys try this. Try it. Solve 5 to the 2x equals 25 to the 3x plus 2, and come back when you're ready, and we'll go over it. Okay, so 5 and 25. They are both powers of 5. So 5 is already 5. 25 to the 3x plus 2 is really 5 squared. 5 squared to the 3x plus 2. So on the left I have 5 to the 2x equals, on the right I'm going to distribute that 2, and I'm going to get 5 to the 6x plus 4. Now I can set the exponents equal to one another because the bases are the same. So I'm going to subtract 6x on both sides, and I get negative 4x equals 4. Divide by negative 4, x equals negative 1. Okay. All right, so let's try these together. Let's rewrite these with like bases. These both have a base of 5. The square root of 5 is really 5 to the 1/2. That means x must equal 1/2, and there's actually no solving to do there, so that's good. But look at this one. Of 2x equals negative 100. What you'll notice first is that I don't think that they have a like base in common that we could convert it to. But the next thing you notice is that there's a negative in front of the 100. So we're saying 2 to some power equals a negative 100. Well, that's not possible. If you will recall, the range of exponential functions is from 0 to infinity, which means it's not negative. Not on its own like that. So there's no way to solve this one. So in this case, there's no solution to this equation because there's no number you could put in for x that's going to give you a negative 100. All right, so we talked about solving exponential equations with the one-to-one method and by making like bases. But now we're going to use logarithms to solve them. So given an exponential equation in which a common base cannot be found, solve for the unknown. So if you can't find a common base, like in that 2 to the x equals negative 100, we couldn't find a common base. So potentially you could try to solve it this way. So what you're going to do is you're going to apply the logarithm of both sides of the equation. So if one of the terms in the equation has base 10, then you're going to use a common logarithm. If none of the terms in the equation has base 10, then you're going to use a natural logarithm. So you're going to take the natural log of both sides. And then you're going to use rules of logarithms to solve for the unknown. So some of these get really interesting. Let's look at this first one. Solve 9 to the x minus 10 equals 11. So for this one, 9 and 11, I don't know of any bases that I could rewrite them as where they would have a common base. So we're going to take the natural log of both sides. So basically I'm just writing ln in front of it. Right? Now, if you think back to the last section, we covered properties of logarithms. That's what we're going to use here. So if you will remember, that you've got a log of a base with a power, you take that exponent and you move it to the front. So this is really x minus 10 times ln of 9. All right, now there are so many different ways that you could go with this, okay? If you were to go and find a question similar to this in OpenStax, they would distribute the ln to both terms here, the x and the minus 10. But honestly, remember your goal is to get the x by itself, yes? So what we could do is, I know that I don't want the ln of 9 on this side because I want x minus 10 by itself. So you can divide both sides by ln of 9. And that leaves x minus 10 equals ln of 11 over ln of 9. And actually, I want to go ahead and erase these parentheses because I don't need them. And then you want x by itself. You want to get x by itself. So what would you normally do? You would add 10 to both sides. Okay, so the answer is ln of 11 over ln of 9 plus 10. And honestly, depending on how you work it, you could make it look all kind of different ways. All right, there are all kind of different formats you could end up leaving it as. But what you could do is just take this and go into Desmos or to go into a TI. And so just to recall, if you're doing Desmos, you'd hit Functions, and then you would hit the natural log under miscellaneous. So let me remind myself what it is. ln of 11 plus over ln of 9. So ln of 11 divided by, you can also, instead of hitting the functions, you can also type out ln like that. And then the whole thing you're going to, I believe we're adding 10. Yeah, we're adding 10. So we're going to do plus 10, and we get 11.09. I'm going to round to 4 because in the homework they were rounding to 4 a lot. So 11.0913. Now, if you go back and you look in OpenStax, they will leave this in an algebraic format that may or may not look like what I have here. However, it would be equivalent to what I have here. Okay, I'll just say that. So you can always, if you want to go back in OpenStax and do extra practice, you can always get your decimal answer, and then if the OpenStax is giving you an answer that is an algebraic form, then you can just type that into your calculator. But basically, it's an expression like the one I have highlighted here instead of a numerical answer. So you could actually put that expression into your calculator and see if you end up with the same solution decimal wise. Now, Newton, they have you go all the way to the decimal. So that's what we're going to do here. Okay, so let's look at this next one. It's 2 to the x equals 3 to the x minus 1. So 2 and 3, they don't have any like bases in common, so I'm going to take the natural log of both sides. Alright, and then the first thing we do after that is we take our exponents and we move them to the front. So this is really x times ln of 2, and then x plus 1 ln of 3. Okay, so this one, I would distribute this ln of 3 on this one. I don't know that we can get around that, so let's go ahead and do that. X times ln of 2 is equal to x times ln of 3 plus 1 times ln of 3 is just ln of 3. And then I want the x's on the same side, so then I would subtract x ln of 3 on both sides. And I get x times ln of 2 minus x ln of 3 is equal to ln of 3. And then you want the x by itself, so you have to get creative. So here I would factor the x out because there's an x in both terms. So I end up with ln of 2 minus ln of 3 equals ln of 3. So at this point you want x by itself, so you can go ahead and divide both sides by this if you want. You could also rewrite this as 1 logarithm. This would be ln of 2 over 3 because of the quotient rule for logs. Alright, so then we want, this is what we have here. Let me just rewrite the whole thing so that we're not confused. So what we would do is we would divide both sides by ln of 2/3. Alright, so let me show you, since we did decimals last time, let me show you how you would type it into a TI. So let me find the TI calculator. So ln is on the left, so ln of 3, close parentheses, divided by ln of, I think it was 2/3. Let me double check. 2/3 it is. Negative 2.7095. All right, so we're going to stop here and we will pick up with part 2 in the next video.